So biochemical oxygen demand can come up as an exam question, and it came up in 2013, so let's look at that question now. The question says, in an experiment to measure the dissolved oxygen content of a river sample, a small amount of concentrated compound A followed by a small amount of concentrated solution of alkaline potassium iodide were added to a bottle filled with river water. These additions were made using the methods shown in the diagram, avoiding the addition of bubbles of air. After both additions, the stopper was replaced carefully and the bottle was inverted several times to ensure thorough mixing of the contents. A brown precipitate was observed at this stage. About 1 centimetre cubed of sulfuric acid was then added, allowing the acid to run down the inside wall of the bottle. Again, the bottle was stoppered and inverted several times to ensure thorough mixing. So, Part A asks us, it says, why is it important to avoid trapping air bubbles each time the stopper was inserted into the bottle and when using the dropper? So we discussed that already. It's to prevent an increase in the oxygen concentration. So that's enough to get you 5 marks there. Part B then asks you to identify compound A, and compound A is a concentrated solution that's added at the start of the experiment, and that is your manganese 2 sulfate. So your manganese 2 sulfate. This can be written in word form, or you would get marks if you gave the chemical formula MnSO4, so whichever suits you better. Part C asks us what was observed on the addition of the concentrated sulfuric acid followed by the mixing of the contents in the bottle. So a brown colour would be observed, a brown colour, and i.e. precipitate dissolves. So brown colour observed will get you full marks there, and the precipitate dissolving just explains where that's come from. So let's look at Part D now. Part D asks us, describe how the burette was rinsed and filled for use in the titrations. Now this is worth 15 marks, so you're going to need 5 points. So, how is it rinsed and filled? So, I would split this into 2 parts. So, the first part would be, how is it going to be rinsed? So, I would say, first, it must be rinsed with deionized water. Then, I would say it needs to be rinsed with the thiosulfate solution that we're using. Then you can move on to filling. So the first thing I would say is clamp the burette vertically. Then I would say fill using a funnel. I would say ensure the part below the tap is filled. And the last point, ensure the bottom of the meniscus is in line with the 0 mark. So I've given 6 points there, just to be sure of myself. You only need to give 5 to obtain full marks. Next is Part E, and Part E asks you to name the indicator used in the titration, and the indicator used is starch in this experiment. Part F is a calculation, so I'm going to skip that and do it on the next slide. So I'll move straight on to Part G. It says, what conclusion should have been reached had a white precipitate been observed instead of a brown precipitate after the addition of the reagents to the bottles of river water? And that basically means that there would be no dissolved oxygen present in the bottle, and this may be an issue specifically for the second bottle that you leave for 5 days, as all of the dissolved oxygen may disappear. Part H then asks you, kits designed for use in the field allow the dissolved oxygen concentration to be measured immediately on collection of the sample. Why is the immediate determination of dissolved oxygen considered best practice? And the answer to that is it prevents errors due to respiration and photosynthesis, as respiration may occur due to bacteria present in the water, or photosynthesis may occur due to maybe some plant parts getting into the water upon collection. So now let's look at part F and do the calculation. So just before we do the calculation, I'm just popping in this flow chart here to help you with your titrations calculations by first principles. So the first thing you'll always do is you will find the moles of your standard solution in the titra volume. So the standard solution is the solution that you know. Then you find the moles of your unknown solution in the titra volume, and I would say the key thing with step 2 is just use your ratio. And for part 3 then, you find the molarity of your unknown solution. Some of you may use the M1V1 over N1 formula and M2V2 over N2 formula. You may use this in class, that's fine to use, but it hasn't worked in the past 3 years, so from 2017 to 2020 you haven't been able to use that. You've had to use first principles, so I would definitely suggest that you practice lots of questions on first principles to try and get used to it. Any of the titration questions that can be done using the formula can be done using first principles, so I would recommend first principles. So for part F, to start, you are asked to calculate the concentration of the iodine in the sample bottle in moles per litre. So I'm going to do this by first principles. So the first step of first principles is to find the moles of your standard solution in the titra volume. So what you need to do is you need to do moles per litre multiplied by your titra volume, and you need to divide that by 1000. So it's the moles of the standard solution that you're looking for here. So we know that our standard solution of thiosulfate has a molarity of 0.02 because that's what it tells us in the question here, 0.02 moles. So we get 0.02 multiplied by the titration volume, which we know from here is 9.4, multiplied by 9.4 and divide that by 1000. And the answer we get there is 1.88 by 10 to the minus 4. The next step is to look at your ratio. So we have, from our balanced equation, you can see that we have 2 thiosulfates for every 1 iodine. So 2 thiosulfates for every 1 iodine. So it's a 2:1 ratio, but we don't have 2 moles of the thiosulfate. We have 1.88 by 10 to the minus 4. So to figure out how many moles of iodine, you use your ratio. So you divide by 2, the 1.88 by 2, and you end up with 9.4 by 10 to the minus 5. Then you can move on to step 3, and step 3 uses the formula of moles multiplied by 1000 divided by your titra volume. So you use the moles for this that you use. This moles here is the moles of your iodine that you've just figured out. So that is 9.4 by 10 to the minus 5. Multiply that by 1000 and divide by your titra volume, which I've already done here. Your titra volume is 200 centimeters cubed, so divide that by 200 and you get an answer of 0.00047 moles per litre. So for F part 1 then, if we keep reading, it says for every 1 mole of dissolved oxygen in the water sample, 2 moles of iodine are liberated in the experiment. Calculate the concentration of the dissolved oxygen in your water sample. So basically what they're saying here is they're giving you a ratio to start with, and they're saying O2 is to I2, and they're basically saying for every 2 moles of iodine you have 1 mole of your oxygen. So if we create this for part 1, O2 to I2, it's a 2:1 ratio, but we don't have 2 moles of our iodine. We have 0.00047. So you should divide that by 2 to find out how many moles of oxygen there is. And when you do that, you get that there is 0.000235 moles of oxygen. So that is your answer there for part 1. Part 2 asks you to find that then in grams per litre. So we know to go from moles to grams that you must multiply by the molecular mass. So you do your 0.000235 and you're multiplying here by the molecular mass of the oxygen, because it's asking you in the question specifically calculate the concentration of the dissolved oxygen. So that's how you know you have to multiply by the molecular mass of your oxygen. The molecular mass of your oxygen is 32. So that gives you that there is 0.00752 grams per litre. And I've just written in there that the molecular mass of oxygen is 35. Then for part 3, which is the last part, it asks it for you in parts per million. And if you remember, we know that parts per million is the same as milligrams per litre. So we have 0.00752 grams per litre. So we already have the litre. So to get it from grams to milligrams, you have to multiply by 1000. And that will give you 7.52 parts per million. So that is your dissolved oxygen exam question. So I'd recommend you go back over that and make sure you understand it fully. So hopefully this video helps you understand the detail needed for a biochemical oxygen demand exam question.